Hey guys, I'm sorry I'm not there today. Let's start with 6.5. We're going to do more with radicals. So we're going to start with talking about the product property. This basically says that if you have a root and underneath you have two things that are being multiplied, you can basically separate those and do each element separately. We did a little bit of that yesterday. Okay, so here I have fourth root of 32. You take 32 and it's going to be 4 times 8, 2 times 2, 2 times 4, 2 times 2. Because this is a fourth root, we're going to group these by 4s. So this comes out as a single 2. And then in the radical, you have one lonely 2 left over. Remember, if it's a fourth root, that's part of the hardware, right? It has to stay as a fourth root. Okay. Now let's take a look at this one. I have d to the power of 7. Okay, what exactly is that? D to the power of 7 means I have 7 d's. 1, 2, 3, 4, 5, 6, 7. If this is a cube root, that means I need to group these by 3's. So here is one group of 3's. Here is another group of 3's. So one group of 3's comes out. Another group of 3's comes out. That 1d gets left in there. So in the end, what do I have? I have d times d, d squared, cube root of d. Okay. Let's take a look at this one. First, I have the root of 12. Okay, let's see what 12 is. 4 times 2. Nope. 4 times 3. 2 and 2. So these two come out. That 1, 3 stays inside the root. So now, C. We were doing this yesterday. C to the 6, and this is a 2. Remember what we said was you could do 6 divided by 2, so this will be C cubed. Okay, what about the D? You can't divide 3 by 2, right? So let's just do what we did before. I have 3 D's. You can group them by 2's, so one pair of D's come out, one stays in. Okay, what about absolute values? The only one that's even, odd is this one. So C cubed gets absolute values, and that's my answer. Okay, so this is fine with, writing out the 3 D's and then writing out the 7 D's up there. But what if you had, let's say, D to the 51? Nobody is going to sit and count out 51 D's. There has to be a more efficient way to do it, which there is. So we're going to do that now. First, let's tackle the 27. Okay, so 27, 9 times 3, 3, 3. This is a cube root, so I can group them into groups of 3. All those come out as a single 3. Okay, now, what about the y's? So what I have here is 4 and 3. What we were doing yesterday was dividing 4 divided by 3, but we were getting lucky because they would always divide evenly. Well, that's because those problems were devised to divide evenly. I had made them up that way, but it's not always going to be like that. So what happens in this case? When you divide 4 divided by 3, that gives you 1, remainder 1. Okay, this number is the number that comes out. This number is the number that stays in. So here we have a cube root. This says 1y comes out, 1y stays in. Of course, you don't have to write y to the power of 1, but I'm just doing it so we can see it. Okay, let's do the z. For the z, we're going to do 7 divided by 3. What does that give me? 3 goes into 7 twice, and I have a remainder of 1. This is the number that come out. This is the number that stay in. So this is going to be z to the power of 2 outside, z to the power of 1 inside. So finally, this is 3y z squared cube root of y, z. And there is no even odd situation here, so that's the final answer. Okay. When you have a quotient, it's a similar situation. If you have a fraction inside the root, you split it up. So you do the root of the top, the root of the bottom. The problem, though, is when you have a root inside in the denominator, you have to rationalize the denominator. Okay, so let's see what we do. If you have something like this, 1 over root b, you have a root b on the bottom. So what you have to do is you have to multiply top and bottom by root b. Okay, so for example, if you have 5 over root x, we have to multiply top and bottom by root x, root x. Why does that work? Well, in the numerator, that gives me 5 root x. But what does that give me in the denominator? Why is it that that works? Because when I multiply these two out, I get x times x, x squared. So do you see how on the bottom now, you have 2 x's, and that's enough for them to come out of the square root as just an x. Okay, so that was fine if it was a square root. What if it's not a square root? What if it's an nth root like this? Then you have to multiply by the same nth root, but you have to modify that exponent. Okay, what am I talking about? Let's see what we have here. 3 over 5th root of 4. Okay, but what's 4 really? Let's split it into the base from which it came. 4 really is 2 squared. Okay, now in order to get rid of this root in the bottom, this is a 5th root. I need to have 5 2's total underneath for them to come out. Okay, I have a couple missing. I only have 2. I need to multiply by 5th root of something. If I only have 2 in here and I need a total of 5, I need to multiply by 2 to the power of 3. And I multiply the same thing up there. Okay, let's see what that does. In the numerator, I have 3, 5th root of 2 cubed. In the denominator, I have 5th root of 2 2's here, 3 2's there, total of 5 2's. So now, this is 3, 5th root of 8, 2 cubed, over all this comes out as a single 2. Okay, so let's do another one here. I have a root, and inside I have a fraction. First thing I do is I split it up. Root 1, root 9. Now it becomes 2 mini problems that I can solve separately. Root 1 is 1. Root 9 is 3. We're done. Here, root 4, root x squared. Root 4 is a 2. Root x squared, 2 x's come out of the square root as an x. I'm done. Okay, here. Cube root of x to the 6th, cube root of 27. Here I have x to the power of 6 over 3, 2. Here, cube root of 27. You can actually, if you forget, first try it out with the calculator like we discussed, and that's a 3. Okay. Root 16, root 3. Root 16 is still 4. Okay, over root 3. Now I need to get rid of the root 3. So I multiply bottom by root 3, top by root 3. So I get 4 root 3 over What is this? Technically, this is root 3 times 3, which is 9. So that becomes 4 root 3 over 3. Some of you might be able to go from here immediately to that step, and that's okay. All right. So when you have more complex radical expressions, how do you simplify them? Well, basically, you have to make sure everything is as simplified as it could be, and there are no radicals in the denominator. So let's take a look here. Okay, I have 5 times a cube root times a cube root. Whenever you have separate roots like this, it's best to combine them. So the 5 stays here, times the cube root of 100 times 10 is 1,000. A squared times a is a cubed. Okay, now this is 5 times. Cube root of 1,000 is 10. But again, if that is not something that is immediately clear to you, just plug it in. All right, so that's 5 times 10 times cube root of a cubed. That's just a to the 1, right? Remember, many ways of doing that. The easiest way is 3 divided by 3. That gets you a 1. There is no even odd situation. This is just 5 times 10, 50 times 8. All right, here, we're going to multiply the 6 and the 4. That gives me 24. Now, inside the square root, I have 8 times 2, c cubed times c. That's a total of c to the 4. D to the 5, d to the 3. 5 d's here, 3 d's there, 8 d's total. This is 24 times root 16, 4. Okay, what about the c? 4 divided by 2, c squared. What about the d? 8 divided by 2, 4. Okay, multiply these. 24 times 4, 96, c squared, d to the 4. Okay, these two problems had a multiplication symbol in between them. You were multiplying the radicals. These ones here are different. These are being added or subtracted to each other. So this is going to be a little bit different. So what we're going to do first is this. Each one of these is a mini problem. This one is a separate problem. This one is a separate problem. We're going to do each one separately and then combine. So here, I have 4 times root 8. What's root 8? 2 times 4, 2, 2. A pair of 2's come out. 1, 2 stays. Plus 3 times. Now I have root 50. 25 times 2, 5, 5. A pair of 5 comes out, 2 stays in. Okay. I have 8 root 2 plus 15 root 2. Now look, the roots are identical. If they're identical, they are like terms. That means I can just combine the coefficients. 8 plus 15, 23 root 2, and that's the answer. Okay, one last one. So I have 3 times root 45. So let's do root 45. That's 9 times 5, 3, 3. These 3's come out, 1, 5 stays in. Minus 5 times root 80. 2 times 40, 4 times 10, 2 times 2, 2 times 5. Okay, what's going to come out? A pair of 2's and then another pair of 2's. So times 2 times 2, root 5. Oh, I actually need to erase this. It got in the way. Sorry, 80. Okay. Here, I can put it back here. Okay, next I have plus 4 times root 20. 4 times 5, 2 and 2. This 2 comes out, 1 5 stays in. All right, so I have 9 root 5 minus 5 times 2 times 2, 20 root 5 plus 8 root 5. Okay, they're all root 5, so I got to add the coefficients. 9 minus 20 plus 8, that's going to be negative 3 root 5, and that's the final answer. All right, so sometimes you might simplify and you might end up with something like, 7 root 5. Oops. My goodness, why can't I? Okay, you might end up with, let's say, 7 root 5. Oh my gosh, I can't write all of a sudden. Oh, my pen froze. That's so weird. Okay, okay. We can talk about that in class. It doesn't want us to talk about this. I guess it'll be confidential. One more thing to be confidential. But basically what I was going to say is if these roots are not identical, then you can't combine them. Okay? All right, that's it. And you can go ahead and start on the homework.